Good morning, everyone. My name is Timur Krzysztof. I'm a contractor for Valve. And today I'm talking to you about mesh shaders, how to use them, what best practices are there. And let's start with giving you a brief intro on what mesh shading actually is. And after that, I'll show you how it's typically used. What are some of the pros and cons compared to the old graphics pipeline? And if there's time, I might also show you a demo. There might not be time, but we'll see. So who here in the room used mesh shaders so far? Or who here tried to look into them? And who had a good experience doing that? Okay. Nice. Okay, so what is mesh shading? There are some good and some bad things here. The way to think about mesh shading is that it gives you a new programming model. And this new programming model enables you to get some efficient geometry processing if you have very high details in your scenes. By very high details, I mean lots of triangles and vertices. The bad part is that you have to pay more attention. It might be difficult to integrate into your existing systems, and it might be also difficult to achieve better performance. So it's not a silver bullet that you just use mesh shaders and you automatically get better performance. It's not that. It allows you to get better performance, but it's not something that you get automatically. So you might need vendor-specific tweaks, and you might need to follow some best practices. So what's this new programming model? Mesh shaders are compute-like. By that, I mean that they operate similarly to a compute shader. That means they operate in workgroups. They have access to various system values that were only available on compute previously. And the main difference that you have to understand between the mesh shading pipeline and the old pipeline is that the old pipeline is kind of a pass-through thing. So you have some input vertices and primitives, and those are the same as the output. So you make some vertex attributes, but you can't change the topology. You can't add vertices, remove them. But with mesh shaders, you have to create your vertices and primitives. And it's up to you how you do that. So there is no fixed function bottlenecks in mesh shading. There is no input assembly. There is no tessellation. It's all up to you. So this is very low level. It exposes you to low levels of the hardware. And that also means that this programming model is not yet suitable for tiling GPUs. So that means if you want to use this for mobile, there are some people here from ARM. You should let them know that you're interested in this, and maybe that will motivate them to do something about that. How does this new pipeline look? So this is a graphics pipeline. It's the same API that you had with the old one. But instead of using a vertex shader, tessellation, geometry, you use a mesh shader. You're not allowed to mix the two. So one pipeline can only have mesh and task shaders or the old shaders, but not all. So this version, it's the simpler one. You have a mesh shader, you have a fragment shader. This is actually not recommended. So you can do this, but you shouldn't do this. What you should do is use the slightly more complicated version. So here you have a task shader. In this case, the draw call specifies the task shader workgroups that you launch. And from the task shader, you have to emit how many mesh shader workgroups you want. And actually, this is what I recommend you to do, because task shaders allow you to make your pipeline more efficient and reduce the work. So what exactly is a task shader? The main task of a task shader is to determine how many mesh shader workgroups you want to launch. And in addition to that, they have an optional payload output, which you can use to pass data from the task to the mesh shaders. And the mesh shader, as I already described, it has this compute-like programming model, and it feeds the rasterizer directly. What are some of the typical uses? So there are two things that we usually mention. First one is meshlets. I think some people yesterday already showed you some of that. So what a meshlet means is that when you are building assets for your game, you instead of working with the full thing, you split your geometry into a smaller group of primitives. And these smaller groups, they are called meshlets. The other interesting thing that you can do is procedural geometry, which means that you might have some kind of an application where you have a mathematical formula to generate your vertices and primitives. I spoke to a gentleman here yesterday who uses this for seafloor simulation. Is that correct? Oh, yeah, right. Yeah, so that's exactly a very nice use case for this. And that means you don't really have any inputs, right? You don't need to input any vertices into it. You just generate them on the fly. It's very nice. So let's talk about meshlets, because I think that's what the majority here are interested in. So you take a larger model and you subdivide that into small clusters of triangles. And you have to pay attention how you do that. And I think yesterday we already saw that it matters. So thank you for mentioning that. So one thing that you have to decide is how large do you want your meshlets to be. The maximum is 256, which is typically what most GPUs allow you to do. But you might not want to go that big. You might want to go a bit smaller, so like 128 perhaps. And the way these are processed is that typically the recommendation is one mesh shader workgroup should process one meshlet. And if you look at the task shader stage before that, one task shader invocation should process one meshlet. So the idea here is that the task shader looks at the meshlet as a whole and determines whether it should be rendered. And then the mesh shader would go into the details of that, and it would look at each primitive and vertex and decide what to render. Here is this bunny. This is actually taken from NVIDIA with permission. So this is a good example of how meshlets might look. Also, if you look at this, it might not be the most optimal way to subdivide this, but it's one way to do it, and it's a good illustration. How do you use this new API? So you make a pipeline, and then you have to use one of the draw calls here. So you have direct draws and the two indirect ones, which correspond to the pre-existing draw calls you have in Vulkan. The typical way that the task shader executes is that one invocation processes one meshlet, and then the whole task shader workgroup, like all invocations in the workgroup, they cooperatively decide how many mesh shader workgroups to launch. And for that, you have to use this emit mesh tasks ext intrinsic in your shader. After that, the mesh shaders are launched. And here, typically, one mesh shader invocation processes one, maybe two vertices and primitives. So the first thing that a mesh shader has to do is determine how many vertices, how many primitives does this meshlet have. And then in the shader, you should call this setMeshOutputs ext, and that will allocate the space for those vertices and primitives. After that, you can write the vertex data and the primitive data to these output arrays. And the most important thing here is there are various preferences in the drivers. So if you look at the recommendations from vendors, they are going to tell you something else. So if you look at what NVIDIA recommends and how to get the best performance for mesh shaders on NVIDIA, it's not going to be the same as for AMD. And in Vulkan, we actually tried to do a better job of representing that in the API. So we have these driver preferences as device properties in Vulkan. So you don't have to make a separate shader for the different vendors. You can check the device properties, and you can make the shader based on that. So hopefully this is less hacky and easier to see what's going on. What kind of preferences are there? So one thing is that a driver might be more optimal if your vertices and primitives are compact. So that means that you don't have gaps in the array. It's contiguous. And the other preference is that AMD, for instance, recommends that you should always use the local invocation index to address these output arrays. And of course, both vendors have recommendations on what's the optional workgroup size for these stages. So when you're writing an application, the best thing you could do is you can look at these preferences and you can make your shader so that it can conform to both of those preferences. So typically, NVIDIA will tell you that you should use small workgroups. I think it's like workgroup size of 32 or something like that. And their suggestion is that you should process several vertices and primitives, so like 2, maybe more per invocation. But AMD recommends something else. So their recommendation is that you should only process 1 vertex, 1 primitive per invocation, and you should have a wider, larger workgroup. So how do you do this? Because it looks like this is a conflicting requirement. How do you write something that can work with both small and large workgroups? And here the solution that we recommend is that you write a loop, but you base this loop on compile time constants. So the recommendation is that you check the driver preferences that I mentioned before, you use them as constants in your shader, and then you write a loop. And then the result is going to be that because it's a compile time constant, the compiler is not actually going to emit a loop, but rather it will emit optimal code on both vendors. So typically what you would do inside a mesh shader is first you have to do some pre-processing where you determine how many primitives, how many vertices you are going to have. So in order to do that, you might do per primitive culling. That means you might delete some triangles that you have. If the driver preference requires it, you might need to compact the result. After that, you call this intrinsic. And finally, you compute all the other attributes and write them to the output arrays. So this is typically how we recommend people to write mesh shaders. Let's talk a little bit about task shaders. What can you do with the task shader? These are some examples that we recommend for that. So what you can do is, even before looking at any individual triangles, you can look at the meshlet as a whole and you can cull it. So cull, that means that you delete it. You don't have to render it. You don't have to process it any further. So one example that we saw for this yesterday is you can have a bounding box for the entire meshlet, and then you can use that to quickly determine that the meshlet is not going to be visible on the screen, so you don't have to launch any mesh shader workgroups to deal with that. Other uses would be level of detail selection, geometry amplification, and also task shaders might be a good replacement for these compute prepulses that some games have. So some games have this trick that they run a compute shader before a graphics pipeline, and they do primitive culling in the compute shader. And considering the traditional pipeline, that's a good thing, but task shaders make this unnecessary. And in addition to that, inside the mesh shader, you can do per triangle culling. That might not be necessary, but if you have lots and lots of triangles, it might still help. And also, another kind of application might be that you don't have any inputs, so you just do some procedural generation. And then, like, there is no point in culling because there was no input that you can cull. And then you can just generate everything based on a formula. So roughly, this is how it looks like. One task shader workgroup can have several mesh shader workgroups corresponding to that. So one task shader workgroup can deal with basically many meshlets at a time. And then each mesh shader workgroup is going to deal with one meshlet at a time. So what kind of advice can we give you how to use this? So you should definitely use task shaders for culling and level of detail selection. So if you want to integrate mesh shading into your application, and if you want to get good performance out of that, so if your goal is to make something that beats your previous thing, you should definitely use task shaders. And you should follow the driver preferences. Other than that, if you really want to go the extra mile, you can also implement other stuff. So if you have all the meshlet data, you can also implement a fallback so that you can also use that data with Vertex shaders. Of course, then you lose the advantage that you would get from task shaders, but at least you have something that works on old hardware. And another thing that all vendors recommend, and I recommend it too, if you use geometry shaders, you can replace that with mesh shaders, and I guarantee it's going to be faster. I mean, I'm not aware of any implementation where geometry shaders don't suck. If anyone knows such an implementation, let me know, but I'm not aware of them. And after you did all that, Mike, our colleague here already showed that you should also investigate what's the best way for you to build meshlets, because it matters. So the bounding box of the meshlet should be as small as possible, because if it's spread out, then it's less likely that you can just cull it. And if you did all that, and after that you still have a lot of triangles, you should consider per primitive culling. But this is not the first thing you should do. So if you look at like articles online, many people recommend to start with this, but I don't recommend that. So I think it's a good thing to do if you really need that, but it's not the most important. The most important is task shader based culling. So what are the things that you shouldn't do? Well, you might get the idea that why the hell do I need an additional shader stage when why don't I just use the mesh shader for culling the meshlets? But that's a bad idea, because you still waste compute resources to launch all those shaders. So that's just not what you should do. Use task shaders, please. And if you use task shaders, you might look at them and you might think that, well, they have this task payload thing, so hey, let's use that. But yeah, sure, you should use that, but you shouldn't overuse it. So that's not meant for passing geometry data between the two shaders. You might pass some pointers, maybe something that helps the mesh shader figure out what to do, but don't overuse it. And the other thing is you should not abuse mesh shading to do generic compute work. That's not really what it was meant for. I know that some people kind of advertise it like that, but no. Also, don't try to disregard these vendor preferences. And if you use task shaders, then the whole compute-based culling is superfluous, so you shouldn't do that. And so, yeah, it might sound complicated, but if you disregard what I said before, then maybe you should consider not doing mesh shaders, because then the Vertex shaders optimized by the driver are going to give you better performance than a mesh shader could. Because the traditional pipeline, it has been around for a long time. It's very well optimized now. So if you're not willing to go lower level and understand the details, then maybe this is not for you. So some people disregard this and they still use mesh shaders, and then they are going to go on the internet and write blog posts about how mesh shading is bad. So as a quick recap of all of that, let's do some comparison to the traditional pipeline. So what is the good things about mesh shaders? What's the bad? So the good thing is it avoids bottlenecks on fixed function hardware. It's more flexible. It basically includes the compute prepass because you have the task shader stage. And the advantage from that is that you can pre-compute and discard a lot of geometry very early without wasting resources on them, which also saves you a lot of bandwidth, because you don't want to waste bandwidth on things that you don't see on the screen. I think we had some people here telling us that already, but I have to repeat it here because it's very important. The cons are that this is not really useful on mobile GPUs yet. It's a very low-level tool, so it's a big foot gun. You can shoot yourself very easily with it. And the other thing is that now that you don't have actual inputs in the shader, you have to couple the shader code to your input data format. It might be a con to some people, might not be a con for everyone, but it's what it is. And another con is that you have to consider all the preferences that I talked about before. So what's the difference after all that? What's the difference between a Vertex shader and a mesh shader? So for the Vertex shader, basically, it's a pass-through. So the output topology is exactly the same as the input. You can't really rearrange it. You can't delete from it. You can't add to it. But in the mesh shader, you can do whatever you want. It's completely custom. Also, Vertex shader inputs are very annoying to deal with. I'm not sure how many people actually like dealing with Vertex inputs, but I think it's very annoying. And task shaders are much more efficient than what you could do previously. For geometry shaders, I think it's an easy consideration. Geometry shaders are very inflexible. So if we used them before, consider replacing those. And a quick comparison to tessellation. Tessellation is a fixed function hardware. So it does what it does very well, but it doesn't really allow you to customize it. But if you use a task and a mesh shader, everything is up to you. And you can do that however you want without relying on the hardware doing it for you. And I think we don't really have the time for a demo. But for people who are interested, I definitely recommend checking out NVIDIA's CAD scene demo. This renders some cars, race cars with lots of triangles, a total of 32 million triangles and 16,000 draw calls. That's huge. That's a lot. So I recommend checking this out if you're interested in mesh shading. Any questions?
How does the performance compare to, for instance, I have a tiny and I render?
So the question is, how does the performance compare to the traditional pipeline? And the answer to that question is, it depends. if you follow these best practices, it will perform a lot better. So I think we saw some actual data yesterday from his presentation. So you might want to check that out. And also, if you run the NVIDIA demo, it has performance numbers. So you can also look at that.
I understand that if you do some things like culling and you may get some improvements by just doing it. But I was just wondering about the whole.
It's the same. It's the same. You're doing the same thing on the same hardware, then it's going to perform the same. So if you're not willing to use the new capabilities, then there is no reason for it to perform any different. So if you want to get better performance out of it, you should do the things recommended earlier in the presentation.
I mean, the reason I'm asking is because if we remember our favorite geometry shaders, right? And by just enabling geometry shaders and just having just one triangle, right, and doing absolutely nothing.
Right. Yeah. So the comment was about geometry shaders. Yes, geometry shaders are bad. I agree. If you replace geometry shaders, I think mesh shaders are always going to outperform them. But I don't have any numbers for you.
So I like order-independent transparency and rasterization order guarantees. How does the situation look when you basically make those triangles with your mesh shader and hash shader? With regards to blending order guarantees. So for example, if I'm using a pipeline, what you have is that the pixels produced by a certain triangle will be blended in the exact same order that the triangle is in the index file. Now that you've taken this away, my question is, what are the guarantees there?
So for the same meshlet, we have the same kind of guarantee, but there is no guarantee in what order the different mesh shader work groups are executed. Oh, sorry, the question was about rasterization order guarantees.
Why all the need for geometry shaders? We have published research for one case where geometry shaders outperform many other. So it was rendering, rasterization for overlapping view raster, and for that use case, geometry shaders perform on par with the multi-view tension, and in some cases even beating it. So that is your use case.
So the comment was about geometry shaders and multi-view rendering. Honestly, I haven't looked into that, but I don't know why you mix up the two things. So I think you can use multi-view with or without geometry shaders, right?
Yes, but we compare different techniques, and the geometry shader based on the pretty fast.
Well, I can't comment on that without looking at the exact numbers. I'm sorry.
Any experience with multi-view?
The EXT supports multi-view. So if you use EXT mesh shader, you can use that with multi-view, and yeah, I think it's worth a try, definitely. But I personally haven't tried that.
You mentioned that you shouldn't mix it with culling. My question is, would it make sense to do still compute prepass on a coarser level and then use that for the basically dispatch indirect of the task shaders?
But that's what the task shaders should do. So, so you have the task shader, and that's what its job is. So if you want to do that in the task shader.
But should you reduce the amount of task shaders that spawn by that if you reduce it on a coarser level? Because you still have one.
So you're suggesting to make an even coarser version.
Yeah.
I mean, why not? I didn't try that, but it sounds reasonable. But I think that you will get, so if you consider the effort of doing that compared to the effort that you have to put into the task shader, I think your efforts are better spent just implementing it in the task shader. And if after that you feel that it could be still better, then maybe maybe consider that. Thanks for your attention. They are asking me to leave now.